Imagine being able to time travel through your application's history. Well, that's the power of event sourcing. You might be used to using a database to maintain the current state of an application. Let's say we're keeping track of how many items we have in stock. We have 10 of this item here, so when we receive another 5 of them, we set the total to 15. Event sourcing is when, rather than updating the current state like that, each change is inserted into the database as a new event. We only store facts about the things that have happened. We can then use those events to calculate our current state, or to calculate the state at any given time, for that matter. Once we've inserted the events, we never delete them. When we want to delete anything, we create a new event for that. This means that we never lose any information. We have a full audit log of everything that has happened. In some regulated industries, this is a great benefit that we get for free. Another nice free benefit of this is that you get tons of information that can be used for analytics and metrics without having to build in any extra monitoring or instrumentation. Just by analysing the sequence of events, we can understand how our application is being used, like which features are the most popular, where users drop out of journeys, how long it takes them to progress through the screens. We might even discover where some problems are. When every action is only adding new data and not modifying anything, we naturally solve concurrency problems caused by several processes trying to modify the same data at the same time. If 2 processes want to increase our total, for example, they don't need to read the current value to know whether to increase it to, say, 15 or 22 in this case, and therefore don't need to wait for one to finish processing before we can process the other. Both events are added successfully and the total is calculated afterwards. In cases where we do need to ensure that the state hasn't changed since last time we checked, such as ensuring we don't go below 0 when we remove items, we can simply ensure that no new events have happened since the last time we checked. We can do this with optimistic concurrency techniques, like including a version number on each event and then using a unique index in our database to ensure that we can't insert 2 events with the same version. So one attempt fails, then we can continue on from the next version. When we need to calculate the current state from our database full of events, we could try writing a query to pick out the properties we need from these events. But with many event types and several properties, that's probably going to be too complicated. Another option is to load every single event and apply them in sequence to an object in code that can rebuild the state. As this approach only ever loads the full event and never individual properties, we can store the full event as one blob of data, which massively simplifies our database. Now we can add new types of events and the shape of the events can evolve over time without having to change our database structure. But if we have to load the whole history every time we want to know the current state, this would be pretty slow. For performance reasons, we tend to keep pre-computed snapshots of the application state so that we don't have to start from 0 every time. But these snapshots are not the source of truth. They can always be destroyed and then rebuilt again from the events. Updating the snapshots could be done in a separate background process that continuously applies each event and updates a separate table or database. When we need to know the current state, we can just query that data for the latest pre-computed snapshot. But this representation might be slightly out of date because some events are still being processed. It takes time between writing new events to the database, processing those to build the current state, and then querying that state later. This is eventual consistency. We need to design our application knowing that the data we read might not immediately reflect the changes we've just made in our event store. If we want to avoid this though, we can update these snapshots immediately by calculating the new state at the same time we create the new event and then ensuring we commit both the event and the state change within the same atomic data transaction. This way the representation is always consistent, but the trade-offs are that our writes take longer to perform and we might introduce the concurrency problems that we spoke about earlier. You may have noticed from this diagram that modelling a system this way clearly separates the reading and the writing concerns, which is why event sourcing is commonly seen alongside CQRS. Sending commands will add new events, and then queries can read from a totally different representation of the data. Another commonly combined concept is DDD, where the concept of a domain event already exists and ties in nicely with what we have here. Check out my videos on those topics if you're interested. These ideas all fit really nicely together, but do remember event sourcing is its own concept and it can be used on its own too.